Should we start? 1 minute early, but we have a lot to cover, so let's get started. My name is Jonas Bonér, I'm the CTO of TypeSafe, and we're really excited to see all you people here. It's looking to be a fantastic conference, I think. The reception yesterday was a lot of fun. So many both new faces and old faces. So. I'm going to talk here about reactive application, reactive programming. And it's the really long title that I really wanted to get in was actually Going Reactive Event-Driven Scalable Resilient System Lessons Learned. But it was too long. But it's really about my experiences and sort of why I think we ended up with what we can now call reactive applications and what works and what doesn't work and why. So let's get started. So, as I said, it's really all about sort of lessons learned, and lessons learned through both agony and pain. Lots of pain. So, I shouldn't switch this one so much. Sorry. Yeah, lots of pain. By the way, Lebowski is ongoing sort of movie that we watch at the ACA headquarters almost every month, actually. We at least in the beginning. So we're starting to get a little bit annoyed by it, especially walking around in bathrobes all the time. I think the world of how we write applications now is really radically changing. I mean, there's new demands and new expectations. And, cloud computing, multi-core architectures. I mean, users demand extremely high SLAs when it comes to latency, and there's almost everything is big now. I mean, lots of users, lots of data, big data, and stuff like that. And I think we really need a new way of building systems. I mean, systems that react to events first, event-driven programming. Systems that react to load. They need to be scalable, automatically scalable to really start taking advantage of all these cloud computing architectures we have. They need to be able to react to failure. I'm going to talk about all of these sort of traits in detail. And this to be able to really give users a rich and engaging user experience. And sort of, since it's all about reacting to sort of the new needs and needs that you might not know up front, I think the way I sort of package and call these applications are reactive applications. It's not me. It's sort of a trend that's starting to see as a way of writing this type of applications. So we have the four traits of reactive that we see. The core is event-driven. That's really what sort of enables the rest of the traits. I think without the fully event-driven, asynchronous, non-blocking core, it's really hard to deliver either scalability or resilience, which I will try to argue later. So the agenda here, I'm going to try to show you how we can get there. First, talk about the trade-offs, classic trade-offs in computer science that we sometimes try to forget because they just make things so much harder. And then talk about event-driven resilience and scalability. Okay? So first, starting with the trade-off. There's really no free lunches. And one of the classic ones is performance versus scalability. So when I'm out there talking to clients, etc., they often confuse them. I mean, they say they have performance problems when they really have a scalability problem, and they have the scalability problem when they really have performance problems. And the interesting thing is that there's a trade-off here. If you want extremely good performance, you have to sacrifice scalability and vice versa. Scalability means that something needs to be, you need to do something to actually manage state across multiple cores, multiple nodes. That adds work that will make your application less performant. But from a user's perspective, it actually might appear to be more performant. The most performant application you can write is a single-threaded application that goes straight down to the database and up, right? But that's has zero scalability. So that's something that you should not confuse. It's really two completely different things. And you first decide what do we really have. Latency versus throughput is another one. To get really good latency, low latency, you usually have to sacrifice throughput and vice versa. One classic thing I will talk about a little bit later is batching, for example. Batching means that for the first user, he will have a little bit delay until he gets a response, because you actually queue up results before you hand them off. But the overall response time of the application will be better. Availability versus consistency is another one that's sort of becoming very trendy and popular with all these new SQL databases and so on. The CAP theorem, you probably heard, that you can't get availability and consistency in a distributed system. It's just mathematically proven now. So there's also one thing that we need to sit down and see. And the interesting thing is, for all of these traits, we don't need everything for the whole part of our application. I mean, some part of our application might need consistency in this area, but not in others. So it's not an all in or not. We can actually choose different sort of models for different areas in our application. So, with that said, let's now dive into these three sort of traits of reactive programming, starting with event-driven. So, shared mutable state together with threads, in my view, leads to code that's completely indeterministic and the root of all evil. I mean, Don Knuth was wrong. I mean, this is, I think, way worse. And I really believe that this is something we should try to avoid at all costs. Okay? Use immutable state, please. And Scala really helps us with this. I mean, sometimes mutable state is okay, but you need to be very careful. Immutable state is more safe, okay? Another thing is a small rant, because I just hate it so much, is locks. I mean, locks is usually the tool that you reach for when you have mutable state, unless you know better, that there are better ways of doing it, actually. But locks is a terrible tool. It's too coarse-grained, I think. I mean, a lot of the problems is that locks do not compose, for example. You really, to really fully know how you should use a component that's using lock, you really need to know how that component is implemented inside, which lock is taking, to be able to either, I mean, sort of rely on the same lock, or make sure that you don't take the lock in the wrong order, or so on. So all this, the beauty that object orientation will give us, like this promise of encapsulation, all breaks down when we use locks. You need to really know the innermost details of how it's implemented. It's also easy to just screw up locks by taking too few locks, too many locks. You take locks in the wrong order, you get deadlocks. And error recovery is extremely hard. So as we will talk about in the resilience part. So instead, never block, okay? Unless you really have to. I mean, sometimes blocking can actually yield a better result, but that's very, very rare, I think. Non-blocking is definitely the best default. And I think the blocking is one of the key that both kill scalability and performance. At least if you have more than one user. As I said, if you're single user, blocking is probably the best way to go. But most applications don't have that. So it all boils down to that you should not sit and consume resources that you don't use. When you're idling, hand that off to someone else. When you're waiting for someone else, let some other guy take your thread and do useful work. Okay? Use non-blocking I/O. There's starting to become a lot of decent libraries for that, starting from NIO and up. And use lock-free concurrency. And I mean, you don't need to write that yourself. That's my point here, is that these things are hard, but there's starting to come abstractions now that lets you deal with this without knowing all the low-level details of how things are implemented. The other key thing to event-driven, I think there's two things, that non-blocking and there's asynchronous. Async. So, I would encourage you to use asynchronous event or message passing. Because if you do that, I mean, you're not sort of solving the problem with concurrency and with sort of scaling out to multiple cores and non-blockingness and all that nice stuff. It actually allows you to think of an application at a higher level. You think in workflow, how the messages are flowing in the system. And messages, if done right, it actually has domain value. So it's all about how you think about how your components should interact. And if you do that, then there's a sort of by effect, you will get extremely good scalability and and a very extremely loosely coupled architecture. A loosely coupled architecture that gives you, it's easier to extend, maintain, and evolve, right? And if you have high load to your application, this will actually give you both lower latency and better throughput, in my opinion. Even though this is a trade-off, and still is a trade-off up in the async world. But compared to traditional way of development, I think it actually gives you both. But you have to tune the knobs to which you actually prefer, of course. So I don't know if you've seen Amdahl's law. I think it's a really good way of illustrating what I mean. So on the horizontal axis, on the vertical axis here, we have the speed up of the program, and on the horizontal axis we have the number of processors. As you can see here, if we have in a program, this is the green line here, having 5% non-parallel code, 95% parallel code, you can see that we can expect a maximum of 20 times throughput, and that will reach that around 2,000 cores. Okay, that is the max. Okay, let's think we have an application now that have like 25% serial code and 75% parallel code. This sounds pretty good, right? That's the red line here. You see, then we just cut ourselves down to 4x maximum sort of speed up. Regardless, if we add 1 million nodes, 1 million cores, it doesn't matter. So having this in mind is really important to know that it needs to be event-driven all the way down, if possible. If you do it halfway or 75% way, you can't sort of expect more than a certain amount of speed up, regardless. We're going multi-core. 10 years you will be here. 20 years, we'll be over here. Or I say 10 years, I think we'll have 1,000 cores. So we really need to start thinking about how we can be reactive all the way down. The database world is way behind. JDBC doesn't even have a sort of an async mode. We need to get there. It needs to be all the way down to the database, all the way up. Okay. So to illustrate things, traditional versus non-blocking here. If you have here's some play code that just grabs a feed from Twitter. So in traditional, we do like blocking between the client and server and blocking, then we should go to the database. In the non-blocking world, we're like event-driven, all in async, non-blocking all the way through. And if, for example, if the database driver here is actually non-blocking, we will have 50% speed up or whatever it might be. 50% of our program will not be parallel, And that will give us down here. We can never reach more than two times of the speed up. So you get the point. It's really important to start thinking about these things. So I think you deserve better tools and more fun tools as well. And some of them are actors, agents, futures. FRP started to catch up. I'm just going to go through a little bit about them and why I think they are worth looking at. So actors, most people. How many here know actors? Oh, everyone, okay. Yeah, this is actors. So, but just to say a few words for you, if there was someone that didn't raise their hands, is basically sort of active components that communicate through asynchronous message passing. Each actor has a mailbox. So they are async and non-blocking by default, so you get all the goodness from event-driven programming. It also has a lot of other things on top of it, like you need built-in fault-tolerance model, as we'll talk about later, in more generic terms, but still. And I think it's a great tool. It doesn't solve all problems, and that's also some of the point with this talk, that there is no silver bullet. I reach for actors usually most of the time, but there are certain problems I will not reach for actors. There really are no perfect tools in this world. So you need to have a rich toolbox and know when to use what, basically. Agents is perhaps not everyone knows about. We have those in Akka as well, and they are in Clojure, actually taken, basically ported from the language Clojure. It's a little variation of actors. They are like reactive memory cells. Instead of sending immutable state to the behavior that you have in the actor, you send the behavior to the immutable state you have in the agent. And It's non-blocking, it's fully async. Reads are free, but writes then happen asynchronously backed by queue. So the nice thing with that, with agents, is they compose nicely. They are fully functional. Since you send functions to the agent, you can compose different functions and send different functions to the agent that will then update the state in an atomic fashion. So it's a nice tool to have in the pocket. Futures is another thing that was added to Scala 2.10. We've had them in Akka a little bit longer. It's really nothing new. Been in Scala, been in Java for ages, but that's really a crippled version I wouldn't even want to talk about. It's getting a little bit better, but not much. So futures really, it's actually full-blown programming model. You can spawn concurrent computations, but then what futures really are all about is that they give you a result that's not yet there. And it's not only that, it doesn't just have to wait on that result, you can actually do something with it. You can work with the not yet computed results, compose them, and register callbacks to be notified, etc. like that. And what's nice with them is that they are monadic, and what this means in real, in practical terms, is that you can use them in four comprehensions. So fully async code looks like very easy to read, imperative code. And they also have a model for managing failure, which is nice. So the failure can be reified, and it doesn't just completely just blow up, stop the computation. Instead, you can manage the failure after the computation has been done, etc. So that's nice. Another way of doing sort of event-driven programming is functional reactive programming. That's becoming very, very popular lately. It's one of the most hippest things you can see around here. You see at the bottom here, there's a lot of implementation. RX is one variation of it from Microsoft. Reactive.js is a JavaScript implementation. RX Java is a port of the Microsoft one. If there's one in Scala, it's a multiple in Scala actually. And then we're starting to see that pattern in the web frameworks like Knockout, or JavaScript frameworks like Knockout and so on. What it's really all about is that instead of having, futures are write once, read many. It's basically a sink. You can put the value in and that it stops. Functional reactive programming sort of adds a concept of a stream to that, so you can actually write to it more than once, and you can have sort of observers, listeners listening into that. So it's a sort of functional variation of the observer pattern. But there are some more low-level details. You have signals, and you can attach them to stream of events. The signal gets triggered for each time the event comes in, and so on. What's nice is that it's totally deterministic. So the implementations reorders the events according to a linear timeline. So you can get really good. I say your code becomes totally deterministic. That means that you will run the same every single time. Very similar to data flow concurrency that I won't have time to go through here, but that also has this trait. Believes it's really code that you fully can trust. So on the other hand, it's single threaded, so it doesn't scale that well. But very nice event-driven model, and it composes nicely. So what I want you to do is think in layers of complexity. So everything has a price. Every layer you add has a price. And I would like you to start thinking with, can I solve my problem using declarative, deterministic, immutable tools? A core like that, using logic programming, using functional programming, using, for example, futures, functional reactive programming, data flow concurrency, etc. All those have a very limited applicability. I think you can't solve all problems with them, but a subset of problems they are great for. Okay? If that doesn't solve your problem, you have to layer another layer in your cake. Okay? Then you need to add indeterminism. Okay? But then you should only add it where you really need it, not like locks and threads where you have a deterministic system and then you just throw threads on it and it becomes totally indeterministic. Okay? I think one of the best ways of doing that is adding actors or agents, because then you can control where it should be deterministic or not. You can have these safe islands of actors and the agents that you really know what's going on. Then you have this crazy world where events flow and there's it's not ordering really. And if that doesn't solve your problem, then you perhaps need to add shared mutable state. But then I would say, look at transactions first, okay? And finally, only if you need it, you should reach for monitors, locks, etc. Some things you need to go down to that level, but it's really all down to the level of the operating system, how that deals with things. There's really low-level plumbing. It should not be the way we deal with these things on a day-to-day basis, I think. So that was event-driven. Go resilient. And now I think it's important to know that my view of resilience is really built right on top of event-driven programming. And I think resilience is actually something that the industry have, to a large extent, completely ignored. Resilience is something we add long later, or I don't know, we throw on some clustering, or we turn on clustering with WebLogic server, and yeah, we all know how good that is. So I think, so it's sort of bolted on afterwards, and I think that should not be the case. It should be something that's built into the model. Okay, poor guy over there. Definitely not like resilient. So I think the problem with the way we're used to do, I mean, failure recovery or error handling in Java, C, C++, etc. The essence of the problem is that we're giving a single-threaded control. So in this single-threaded control, you're supposed to do your business logic, and if something screws up, then you need to save this context and do all your error handling right there in that thread of control. Right? If the thread blows up, you're screwed. Okay? And the thing is that if you don't do that, there's no way of even finding out that something went wrong in the system. Oh, the best you will see is like a stack trace all the way up to Java Lang executor service, concurrent executor service, and there's dead silence. No one else found out that that thing broke. Okay? That's broken. And this leads to defensive programming. Since this context is the only thing you need to do the error recovery right there. You have to try catch there, try catch here, try catch here, try catch here. So your program is really completely tangled with the business logic is tangled with their error handling. That's bad for the first part of it, but it's also not in one place. It's like everywhere. And we take this for granted. It's madness. Okay? We can do better than this, I think. And I think the right way is to use bulkheading. That's just an old-fashioned way of dealing with failure management. I mean, it comes from this so that when you build ship, you have these safe compartments, right? So if there's a leak here, this thing it gets filled with water. It doesn't. But this compartment sort of isolates the failure. It doesn't lead to cascading failures like you can see in WebLogic server or another sort of tools that haven't really done this well. So you can manage failure locally, right? And I think this concept, together with supervision, is really the key. Okay? So, use lightweight processes, compartments. I mean, it can be actors and can be other ways of dealing with this. I mean, the important thing is that you have just someone watches this compartment. How is he doing? Okay, and if something breaks there's a notifications sent out to that parent, to that supervisor, say this guy is really behaving weirdly. He's dead, or somebody ran off. Some other doing something he wasn't supposed to do, or whatever. And the event-driven model here comes in that in order to do that, you need to have a way of reifying the error as an event and send that event asynchronously to the parent. So the event-driven model really ties into how this all works. And now the supervise is you have extreme loose coupling between the sort of the manager of and the worker. The manager can actually somehow deal with the failure. He can choose to kill the worker, restart him to a new one. He can suspend him, try to resume him later on. He can restart him. He can do all kinds of things. So he can tell him to try to go the job over there. And the nice thing, since it's all event-driven, As we'll see when we talk more about scalability. And event-driven program message passing is really distributed by design. It has the same semantics local and remote. So this actually does not work in compartments for a single sort of node, but you can actually have this span multiple machines and you can get full resilience in the cluster. And what's even more importantly, I think, from the programming model perspective, it totally decouples the business logic and the error handling. There's no tangling going on here. The business logic is clean, the error handling is clean because they're in two completely different places. Okay. So, scalability. As I said, performance versus scalability. How do you know when you have a performance problem? Okay? I'd say if your system is slow for a single user, then you have a performance problem. Okay? How do you know if you have a scalability problem? That's if your system is fast for a single user but slow when you have a lot of users. Okay? There's a big distinction here. So reach for the right tool by first understanding what kind of problem you have. Okay? So now I'm going to talk about some bad ways of dealing with this. Okay? Transparent distributed computing. It has proven more than once. People don't learn from lessons, right? They try it all over again. But it doesn't work. So distributed shared mutable state is a bad. I mean, shared mutable state, I've tried to make a point, is bad. Making it distributed does not make it better. I think actually instead of having the root of all evil, you have actually evil to the power of n, where the n is a number of nodes. Yeah, do the math yourself. Okay, distributed objects. It's been tried and proven to not work. Okay, clustered objects. I mean, Martin Fowler really hit it when he says that it sucks like an inverted hurricane. Don't even go near those things, I think. Distributed transactions, actually, I'm a little bit on the fence there. I used to hate them, XA, etc. But it's starting to come up some pretty interesting papers how it's actually possible to do really scalable distributed transactions. I mean, like HAT, for example, high available transaction is an interesting paper, and then Calvin is another interesting sort of research project, and so yeah. But that's still my advice. Still try to avoid them. But there might be something interesting there soon in the future. Good reading on this is like Note on Distributed Computing, this classic paper by Waldo. And Werner Volos, the CTO of Amazon, have written an interesting paper as well, six misconceptions about reliable distributed computing. Another thing that I really want you guys to avoid, that has also proven not to work, is RPC. And when I mean RPC, I mean the classic sense of RPCs, emulating synchronous method dispatch on the network. That's a bad thing. It's a bad thing. It tries to help you guys, right, by giving you a familiar model of how you program, right? But it just adds too much magic. And as soon as you go on the network, it's a completely different world, right? And you can't nothing that you take for granted will work. Right, I mean, RPC ignores things like latency, partial failures. You know, the network is inherently unreliable, and then trying to hide that is a bad thing, really bad thing. It's just too much that can go wrong, I think. Good paper here is Stephen Oski's Convenience over Correctness, where he really thrashes that model. Instead, I'd say embrace the network, embrace the network and use, as I said, use an event-driven model for distributed computing. Use asynchronous message passing, non-blocking, and then be done with it, I think. It's really all about, instead of trying to hide all the potential things that can go wrong, and embrace the network with all its constraints and have them first class, because then you can actually manage them. It's not just, oh, something happened, in the black box, let's try again. You can actually manage failures, manage odd corner cases if you expose it into the programming model. And the essence of distributed computing is really message passing. That's really what, when the TCP, UDP, you name it, it's message passing. So I think that it's just wrong to try to layer a level of abstraction. It's just trying to give you an abstraction that leaks so much that it's not useful. Talk about leaky abstractions, this is one. Okay. Guaranteed delivery is another favorite of mine, okay? For delivery semantics that people normally talk about are no guarantees, at most once, at least once and only once, and so on. It's all lies, okay? Because the network is inherently unreliable, and there is no such thing as guaranteed delivery, okay? It's just variations of lying, let's say. Or hand waving, if I would, yeah, it sort of works, but yeah, you know, blah, blah. So, getting to the bottom, guaranteed delivery. The question is really what to guarantee first. I mean, it means different to different people. So, this is going to get ridiculous, by the way. So, but here we go. So, what should we guarantee? That the message is sent out to the network, that is received by the receiver's NIC, that is put on the receiver's queue, that is applied to the receiver, that it starts being processed by the receiver, that it has been completed, reprocessed by the receiver. What do you mean? What do you want? I mean, it's impossible for any vendor to know that. That's use case specific. And each one of these have very different costs, okay? So you don't want to pay for something that you don't want to use, okay? So then what should I do? I think we should add with 0 guarantees, and we should add them one by one as we need them for the specific use case we need them for, okay? Because as I said, different use cases mean different guarantees, mean different costs. And how is that achieved then? So each additional guarantee will either decrease performance, throughput, or scalability. That's a fact, because you're doing more work, sometimes way more work. Traversing the network is very expensive, and it will increase latency. So it can lead to unhappy customers. You might think that they asked for something that they actually didn't. Okay, so I'd say just use acking and be done with it. Acking is extremely simple concept. You can sort of just sign off something whenever you want it. When it receives when it puts on the queue, when it's taking out of the queue, when it's added to the component, when the components have started processing, you can do acking whenever you want. And it's a very simple, very efficient way of doing it. And you can do it for n number of messages. You can signing off 10 at a time if it's okay that you lose n number. You have all the flexibility in the world. Okay, you don't need a lot of fancy products. The products that deal with this automatically, I think, instead of use event-driven programming, asynchronous message passing, and control this yourself if you want to at least write through the scalable systems. Another way is batching, and I took this slide from the CRM chapter in this Architectures of Open Source Architecture. What is it called? Applications of Open Source Architecture, something like that. It's a pretty good book. But I don't remember what it's called, but still, I read it. Anyway, you have the link there. What they try to illustrate there is that if you want to send one message out of the network, you have to traverse first the app, then the underlying sort of driver, then go to the TCP layer, the IP layer, and then down to the NIC. If you want to do that for every single message, that's extremely costly. Batching means that you just have to do the batching in the driver, and then n number of messages you go all the way down. If you would translate this to a Java application, it will look like something like this. You will have the application layer, the NIO layer, then down to the JVM, then you go to the kernel space boundary, the TCP layer, EP layer, Ethernet layer, then out to the NIC. Do that for every single message is insane, right? It's extremely costly. Instead, batch things up, do it once every 10 messages or something, like every 100 messages or so. You will increase throughput immensely, okay? So, latency versus throughput is another sort of classic that ties into batching. Batching is a way of increasing throughput at the cost of latency. As I said before, for the first guy that comes in that's added to the batch, it will take longer for him to get his response. But the overall response time will be a lot better. So it's a trade-off. So how do we know? Well, how do we know what we should do? I think we should strive for maximal throughput with acceptable latency. And this is very vague. And here is where you need to sit down with your customer. and say, what are the SLAs here? What is acceptable latency? And once we have figured that out, then we know how much headroom we have to try to get the maximum throughput. Don't guess, right? Don't guess what the customer wants. Don't guess this. So I try to show you here now then, to build really reactive applications, when you start with an event-driven core, it's really the enabler for both scalability and resilience. And if we add this, we can easily add interactive on top of it to really write this rich, extremely responsive, real-time feel applications. If we write web apps, if we only write backend systems, yeah, this is probably just feeding some REST service or whatever. Okay. So if you want to get started with writing reactive, as James said yesterday, you should definitely download the type-safe activator. It has a lot of, basically has all the tools that I've talked about so far. Just get it ready to get started. We added a whole bunch of new templates for Manaka clustering or distributed pub sub or everything you might name it when it comes to the low-level stuff, slick and stuff like that, but also play and higher up in the stack. So it's a very good way of getting started. So thank you. I've finished in time for questions. If you want to contact me, just drop me an email or reach me out on Twitter. Something. I hope I made some sense. So thanks. Yeah.
So event-driven computation is good because it solves lots of the problems, but at the same time, it is sometimes really hard to diagnose why messages got sent to a certain location. So what are the plans or the current features that will allow you to find out why the wrong message was sent to a specific actor? Or is it just part of the design of the actors that those messages are usually sent to the right people?
Yeah, if you send them a wrong message to the wrong actors, usually by design, somehow there's a bug, right? But we're trying to work hard with tools support that would help that. We have the type-safe console, for example, that annotates every single message that you send in, and you see that visualized. You can see them. You can see, how the actors are doing the mailbox, how they fill up. We haven't added like full graphical visualization of how the messages flow in the system. That's something we're working on now. And I can say that within a month we will release that as totally free for developers. It's been part of our subscription package before, but we see it's immensely useful for developers. We use it ourselves in the company for that. And we don't want to make money on developers, right? We want to make money when you guys make money. So we actually going to make it totally free for developers. That version will not have that full visualization, but you will see that coming later in the year. Or in some months, hard to say when, but I think that is the key, because you say, with all this, as soon as you go async, it's really hard to fully comprehend the system when it's running. I think it's easier when you design it, because it's all workflow and you can easily see how the messages are supposed to work. But if something goes wrong, it's harder. Since ordering is interleaved, etc. Right? So and you don't have like these clean stack traces that go all the way up, which is a good thing, but it makes it harder. Sometimes harder because messages can be lost and stuff like that. However, in Akka, if a message is lost, it's just not just lost. It's always like piped to a dead letter actor queue. Dead letter actor, if you call it, but this is dead letter queue. So you can subscribe to those messages through our event bus. And manage them. So there are many ways you can try to deal with it, but it is a real problem. I agree, and it needs to be addressed.